Okay, let us leave it as it is. The title of this contribution is Time-Dependent Routing Model of Software-Defined Networks, and it is based on diffusion approximation approach. There are 4 authors of this work, Erol, Gelenbe, and me, and 2 our PhD students. And we work in the Institute of Theoretical and Applied Informatics of Polish Academy of Science, and also at Silesian University of Technology in Gliwice, Poland. And this work is also a part of, a very small part of our work in secure and safe Internet of Things, a European project our institute is coordinating. So this is a model of software-defined networks. These networks, which are seen by some people as a future of Internet, have a particular structure. There's a central controller that has information about the traffic in the whole network and changes routing following the current situation. This implies, if we want to model it, time-dependent routing and transient state analysis. Transient state analysis is quite difficult in standard queuing models. So we are trying here diffusion approximation. It is an engineering approach in the sense that we are using existing method, very classic ones, I may say, introduced in 1970s by Erol, Gelenbe, and Hisashi Kobayashi. So mathematically, there's nothing new. Our effort is to make of these methods, or this method, a tool that is useful in well modeling real cases. So to test if these models are performant for parameters we may encounter in real networks. And it turns out it works. The model are suitable. And we are seeing from some numerical examples that transient periods in such models take a large part of the entire time of a network is working. So indeed, the transient analysis is necessary to see its behavior properly. Once again, software-defined networks are quite a new experiment, and well, there is a controller and there are routers that are controlled by this central controller. This is a scheme of one router. The structure is maybe complex, but it may be simplified. So here we have, on the left side, we have input queues. They are analyzed by arbiter and put to the packet buffer. And the main service is to determine by examining the headers of the packets to what traffic, to what link, what connection they belong. So there is a table of all existing links, and it is examined one by one, row by row, up to the row which represents the needed link. And then a packet is sent to the output Q. Sometimes there's no proper flow. In these rare events, the packet is sent to the controller or just deleted. So with in fact, we are replacing the whole device by a single queue where the service time is the service time is just the time of examining this table of connections. If it is a linear search, then with here we assume with probability P, it is the time, fixed time to search the whole table up to the end, and with this probability the packet is rejected, or well, the link is not found, or it is uniform distribution between 1 and k lines to be examined with probability 1 minus p. And here k is the number of rows, number of connections, and t is the time to examine one connection, which is constant. So we have a discrete uniform between t and kt. And to describe the performance of this queuing system, we use diffusion approximation as it is defined by Erol many years ago. So process X here, diffusion process, represents the number of packets in the queue. And so the position X or this process X is the number of packets. And the justification of the use of diffusion approximation is that the changes of the process N and the changes of the process X have normal distribution. And if we consider process N, the mean during a certain time or unit time, let's say, the mean is lambda minus mu, and the variance or the changes is lambda Ca square, mu Cb square, which are the squared coefficients of variation of A is inter-arrival time and B is the service time. And beta and alpha are the parameters of the diffusion that represent the mean changes of the diffusion for beta, and alpha is the variance of the diffusion movement. So we take beta lambda minus mu and alpha as here follows, and we solve the diffusion equation. I'm here music, is it all correct?
Yeah, it's fine. You hear the music?
Yes.
Should not
okay,
be here.
okay, just, but
no, here it's everything is fine.
yeah. So I'm here some audio here, but okay, I'm trying not to hearing it. So
yeah,
and,
please proceed.
Okay, okay. But I guess it is on your side, because hearing the accent, it's in English, but I think it's a university something. So, but I continue. So the equation 1 is the diffusion equation, and the first line is just simple diffusion. So this is diffusion movement, and the next line, this is these are jumps from the barrier at 0, because the Q is not negative, so you have a barrier at 0, and Q is limited by n, so we have a second okay, I will diminish the sounds because it's a little bit confusing. Okay, so and now, so we have two barriers, and 0 and n, and these are jumps. So the stay at 0 is the idle period, and the stay at n means the Q is saturated. And these are balance equations for P0 and Pn, probability being any barriers. This is steady state, the solution as given by Erol. And also we may here, so F gives us the Q distribution, whatever is the inter-arrival and service time distribution, just as function of first two moments of these distributions. And here, the first passage time for the diffusion is approximation on the waiting time. So if a new customer comes to the queue and sees the distribution f of x or the queue, the time he is in the system is the first passage time from the position, initial position, from the end of the queue to 0. And some examples of the numerical examples, simple, how it proceeds. Here you have the distribution of the diffusion process, steady state, and for example, x equal 5 means this is well, probability we have 5 customers in the system, and so on. This is delay, this is probability that the queue is saturated, and so on. But we need the transient solution. So it was my idea many years ago to represent the function f, the solution of this diffusion process with jumps from barriers, by a simpler solution I knew how to solve, where the diffusion process is limited by absorbing barriers. This is a standard problem. The function phi represents the density of diffusion movement when we have two barriers, absorbing barriers at 0 and n. This is its Laplace transform, because we may proceed in terms of Laplace transforms. And now the interesting function f, the density of the diffusion process with jumps, here is represented by a convolution of all processes with a function phi, so with the absorbing barrier, which may start before the time t, which is the argument of f, with some intensities g1 and gn-1 and -1. Because if you are in barriers, there are jumps from 0 to 1 or from n to n-1, and then we have a diffusion process that starts either at 1 or at n-1 and adds either at 0 or at n. And here, so the problem is just to determine the densities G1 and Gn-1, that a new process phi is started at a certain moment tau. And we do it having balance equation, what is coming to the barrier, what is leaving the barrier. So we manage to make this balance, and then we have the solution. But it is simpler to have it in terms of Laplace transform. And we have also probability that the process is at 0 or at n, which is the integral of what is coming to the barrier and leaving the barrier. And having this function f of s, numerically, we use a very simple stack-based algorithm. We determine the original or the density function, and it works. We applied it to a network, SDN network router, as described here, and we see some reactions. The solid line is the changes of input flow, and here the response is the mean waiting time. So you see that even if the changes are quite quick, abrupt, the increase of waiting time is not so quick. So all these times are more or less transient times for parameters which are typical to the router. The same for mean delay as a function of rho, so the utilization, or here the Q length as a function of lambda. Each time we see that a transient time is quite important. The time is 1 second, and the changes of flows typically in SDN networks are 0.1 second, 100 milliseconds. Now we go to the network of such stations. I will just signal that we use two types of equations. One equation, 14 here, gives us the output, the input flow. Well, for the intensity of flow, it's quite simple. It's just the traffic equation, so-called. What is leaving all stations is coming to other stations. But for the second moment of inter-arrival times for any station, we use two types of equations. One is the density of inter-departures time from a station J, and we, as a function of what is the service time and inter-arrival time, and we get here the squared coefficient of variation of the inter-departure times. This is one equation. What is the variance of the output as a function of variances of the input and service times, 16. And the other is what is the variation and the input out of a certain station as a function of all output variations of all other stations in the network that are sending customers to the station I. And then if you have the delay at each station, we may have the delay for a certain path between sender and receiver. And also if we have loss probabilities or probabilities that the process is in the barrier for one station, we may compute the loss probability for the whole path of a number of stations. And here, a numerical example that is demonstrating what we are giving. So host 1 is sending packets to host 2. And we have 4 stations, station 1, and then station 1 may send packets directly to station 4. If the flow is below 1,000 packets per second. If it is greater, the packets are also sent to station S2 and S3, and S2 somewhere during the considered period receives additional flow lambda 2. And here presented are the parameters which are taken from a literature. What is the time for this examining the table of flows. The Q is limited to 100 packets. What is the input flow intensity? And some graphical results. So this is lambda 1, blue, the flow coming to station S1, and red is the flow coming to station S2. And the time is between 0 and 1. These are some examples of the Q distribution for station S1. They are in logarithmic scale. Note that we have results also for very small values of the distribution, and that they depend on the variance of inter-arrival times here. No, this is for CA, for the variance close to the exponential one distribution for various times here. And here for a fixed time with variance of inter-arrival time, which is 1, 4, and 8. So we are prepared to see different traffic patterns. Here is the routing decided by the model, let's say, and this is the output flow for each station as a function of time, because this variance of the output flow makes the variance of the input flow for the next station. So it's important to know them. And this is probability that station 1 is full as a function of time. Pn of t, P100 of t for CA1 square 1, 4, and 8. Also note that even very small probabilities are obtainable. This is the Q, mean Q for station and S1 still, as a function of inter-arrival time variance. So for small variance it's red, for larger is yellow, and green for that. And blue is are the changes of lambda. So you see also here that transient times are not finished before the next change of the input flow. Here are once again routing probabilities. Here is the rho, let's say, or we put it rather lambda over mu. So the coefficient of the use of all stations here, because it interferes to the output flow, so we are measuring. So we are displaying here all parameters which are inside the equations we use to solve the network of Qs, in fact. This is square coefficient of variation at the output of Qs S1, S2, and S3. And its changes between 0 and 1, let's say. Because the squared coefficient of the service time coming from the time of searching the table is around 0.3. So it reduces the output flow variances. Here, Pn of t probability for S2, because we may examine all stations by one, or we may examine the behavior of the whole path. So here, station S2 and probability of saturation, which may be also very small. And in function of the input flow variation to the first station, it's second station, but then the variation of the flow, input flow at second station depends on the variation of the input flow at first station, etc. Here This is probability of saturation for station 3. And probability of saturation for station 4, also as a function of the variation of input flow variation at station 1. And then we demonstrate some probability of loss along the whole path, S1, S3, S4, here, as a function of variation of the input flow for station 1 here. And well, a small example of how to optimize. So let us see, we are at the beginning of the interval delta. The routing may be change each delta interval. So what we know the flows and its characteristic at the beginning of interval. And we know the history, which is in the Q distribution we know at each station. So having this information, we may compute the future, how N2 and N3, because we are seeing the system S1 and then S2 and S3, and we should decide what is routing probability from 1 to 2 and from 1 to 3. So we are computing a mean value of the Q during delta at Q2 and at station 2 and station 3 as a function of time, which is inside delta. And we minimize what we call here a backlog in this station. And by minimizing this function psi, we get R12 and R13. And here we have the solution. It depends if station 2 has additional flow or not. If not, well, the station S2 S3 are similar, so it is good to share 50-50 the traffic. But if there is a certain flow coming to the station 2, the probability of routing from 1 to 2 is preferably smaller in this case, as indicated on this figure. To conclude, just say we are able to solve these models, these kinds of models, and to see the behavior of each station in the model. The topology is desired, and also the number of stations may be quite larger in such a topology. So numerically, we mastered it, and it is a contribution showing that diffusion approximation, which is evolving, which is each year adapted to another problem which arises in computer science, also for SDN networks may be applied. So thank you, and I should put the sounds to hear your comments.
Yeah, thank you so much. Thank you so much for your very interesting talk.
Just a moment, I'm still.
Can you check if there is something at your side, maybe, because in the online everything is clear. We only hear the sound.
Oh, it was my fault. Yes, I found the source of the sound.
Okay.
So
thank you again. So currently we are all of us are online. So we applaud virtually, and thank you so much. And let us ask. We have some time for several questions, and I will address my questions at the end. If anyone else has any questions, please proceed. Okay, there is some silence. I don't know. So let me then ask. So it seems that your talk was very somewhat connected to the keynote talk by Jim and also to the talk by Benjamin, because I just observed, at least in terms of graphs, I observed some similarities in the. So in case of Benjamin's, there was no transience, but instead there was some sort of decision-making parameter that was changing, and then the model was adopting, like somewhat like in your case, you showed the graph with this routing probability that is adopting to the flow, right?
Yes.
And in
Yes.
case of transients, there was some, we observed some delay in this adaptation, but in some cases it managed to adopt finally to the steady state, right? And
yes, the idea, well, the reason, well, if the controller changes the flows, changes the routing, and changes the flows, the queues are increasing or decreasing, but the time they attain the steady state is quite large compared with the time of the changes of routing in such network. So, so what should be stressed here, that we have a tool that may model in a natural way transient states. Transient states, if we use classical queuing theory, it's quite complex, and it's tedious and limited to certain cases. Here, for any service time distribution, for any inter-arrival time distribution, we, in a natural way, of course, it is an approximation, we have a transient distribution. What are waiting times, what are queues, and on this way, on the basis of this information, the controller may take a decision for the next period.
Yes, thank you. And maybe a few comments, maybe a few words on the, so since there is this optimization problem, maybe what do you think, can this sort of neural networks or all these modern tools for solving these optimization problems, can they be used here in order just to optimize, to obtain this optimal decision in some sort?
I think yes, is the next level. We are furnishing a tool predicting what is, if the routing as such and such, what are the delays, what are probabilities of losing a packet, and now the higher level is to make a well, a box which optimize the network.
Yeah, oh, great. Thanks again, and thank you so much for your interesting talk and for your answers. So,
thank you. Thank you indeed. It's my pleasure to be here.
Yeah, thank you.